We've learned before about this example, which is basically just to change, to change the weight or the force, from one to x-axis and to y-axis, decompose, and this is some example. Still, the main formula is simple, but to apply, you need additional knowledge from math, trigonometry, and from high school math as well. And this is what the last time that we were discussing this example. This one is also an example. This one example, sine, cosine, and then I explained a bit about this just for a few minutes. So we're going to continue with this. The moment of force. Object subjected to force on certain path can rotate. So, because now we see that the position of the force can make effect of the stuff, the goods, to rotate. Kind of rotation effect. Even though if we do apply it, it will fall, but it's actually basically rotation. Right? Rotation. The axis of rotation is a point or a line that is not passed or intersect, and it is not parallel to working line. So the axis of rotation is usually the axis that we want to see. What's the moment? What's the moment? And also usually it's the place where the critical point of a structure that we need to know how strong it is, because that structure has to endure this rotation effect. Can it endure? Usually it's just forced to push, to pull, but this one is to push and pull and rotate as well. So it's more complex, and we'll see this. We are still on the simple part, but next week maybe, or we're going to see the inside of a structure. In here, we don't see the structure just any shape, but next week I think we're going to see what's actually the inside of a table or anything. Now this one, F, we have this force F in point B, and then we have point A as the place that can make this structure not moving or stuck at something. Okay. And this force F in point B has a distance to point A as T. So point B, if the point A we held it together, it won't move. Point B might move clockwise if it can move, or it has a rotation effect. So that means point A will need to endure this movement. If point A does not want point B to move, I mean it has to endure or make a kind of force, in this case is moment, equal to what we need to find out, which is the M equal to F force multiplied with the distance. And this distance is not just from B to A, but from a point that is perpendicular. So D, you can say, is not from B to A, because from B to A, this line of force is not perpendicular, while this one is 90 degrees, approximately. It is. But the D, if you don't know the D, you need to find out where is the D. Yes, we need to find out where is the D using this. You need to find out if you need to put a line, this has to be 90 degrees, this has to be 90 degrees. Then you can find the D. Then that's the D, and multiplied with F, you got the moment. It's a Newton meter for the unit. And moment has, we call this equivalent moment. Since F with the transferability principle, we can move this as long as it's still in the line of the force. At point B, we can move it to point C as long as it's still the same line. Yeah. So we can do that, still the same F, and the D, we can find it easier. Okay. This is also D. This is also D. And this is the same F. So point A still have the same moment, has to endure the same moment. Okay. And then I think I give you this last week example. No? Okay, I'm just going to discuss it. Yeah. So this is an example that we have a structure like this, and point D is where this structure is attached to the bottom section. Yeah. And this point on the top of this structure, we have F equal to 20 Newton, going that way, 35 degree, yeah, clockwise from the negative x-axis, 20 Newton. So the question is, determine the moment at point D. That means we need to find this small d, yeah, which is the distance. And it's not from D to this point, say it is point C. It's not here. It's not 2 meters, but somewhere in here. As long as this is perpendicular 90 degrees, we need to find out where is the D. Yeah. And this angle is going to help you. If you know this angle 35, in here is also 35. And how it become like that, it's again the principle of trigonometry and triangles from the basic math. Yeah, you can find out again. Try it yourself. How can this be 35 same as this? Yeah, you can try that. And so now we have this D, the place of the D. But how long is D? We don't know. We need to find out first. But we do know that this is 35. So there you go. Yeah. Cos 35 of cosine is what? This is 35 d by the length of the 2 meters, right? D by this divided by d 2. So if we know, we can just use calculator what is cosine 35. We can find the d, which is actually it's 1.64. So you just need to put the d on the equation. Yes, f is 20, the d is 1.64. So the moment in point D is 32.8 Newton meter. Okay, it's the basic is always simple. To find the d, then you many time. I mean, in the exam, that's the most time-consuming one, to find the d, for example. And this is just one moment. Could be several moments, like several forces. There's a theory that called Varignon theory. Basically, this: the moment of a force to an axis, like this F, to an axis of O, for example, or yeah, is equal to the moment caused by the component of that force in the same axis. It's like the force itself. We arrange this force in F into Fx and Fy to decompose this force with this Fx component in x-axis and Fy component in y-axis. Right? So now we have two forces, Fy and Fx, and each has its own distance, 2.0, which is x for the Fy and small y, and for the Fx. So now we'll have two moments now. So this is another way. You could try to find out this d, by finding out some information as long as you have the angle of this f. Or you can just decompose this f into fx and fy and calculate the two moments. Okay, two moments. It's just that using this moment, you can see this fx toward this axis. It will have a reaction or not reaction, yeah. Make this rotate. Looks like it's going to rotate clockwise. Yeah. If this thing can move from point O, from the axis point O, the center point O, fx is going to move clockwise. While fy, say, this thing, from this center is going to move counterclockwise. That's why here we have fy multiplied with x, which is the moment. And this one has minus. So that means this case, for the counterclockwise, the sign is plus. For the clockwise, because big X multiplied with, or fx multiplied with y is clockwise, is minus. So if using this, I usually add something in the front. Yeah. For that case, I will add plus, which means if it's counterclockwise, it's plus. Clockwise, that means the opposite. That is plus, this is minus. This is, I suggest you always do this, okay, to help yourself, so you won't make mistake in other part of moment of the part of force when you calculate, and also for me as you want to grade, so I know, okay, he's using this. Okay, to be consistent. Because if not consistent, then you're gonna have a wrong result. Okay. This is Lagrangian theory. There is proof, but I want to just skip for now. But you can read it. Why is that's the proof? Okay, it's basically from trigonometry principle, right? So let's now go to this example. Similar example, same example as before, but now we want to decompose the f into fx and fy. Yeah. Still same question from D, and still exactly same data. Now we just need to find out first what is fx and what is fy. Yeah, fx is projection of f to x-axis. So fx is f cos sine 35. 20 cos 35, it's 16.38. While fy, this is also projection of f to the y-axis. It's equal to f sine 35, because this 35 is in the air. That means 20 multiplied with sine 35, we have 11.47 Newton. We have fx and fy. Now we need to know the arm. See, at x we have an arm, which means the distance from this force to the D, to the center, which is 2 meters. Okay, but fy is going through this D, the point D. So it does not have an arm. The arm is 0. That means the moment created by this fy is 0. We do have fy, but the small d on the arm is 0. That's why the fy is 0. While the mx in this case is just this, and this is only because of the fx multiplied with this distance. So just like this. Yeah, this is the result. Okay, so there is two ways. You need to find the d based on the f, or you need to decompose the f into fx and fy first. It should have the same result. Yeah. Is it 32.76 while the previous was kind of, yeah, 32 as well. Yeah, 32.8 in this case. 7, 6. This similar. Okay. Any question? Did I send the PPT?
Yeah, already got.
So this. Is it clear? Okay. So the main point in here usually related to asset industrial engineering is during the quality check or failure. If you have not just quality but it's already in the market and it has failure, you sell bicycle for example, it has failure in certain part, then you want to know that part that fails or that part that is critical for the quality check. You want to know what is the it needs to endure, the weight, the moment, yes, that it needs to endure. So in this case, people will think, okay, D is critical for quality. You want to know in this point what's the force, the moment or weight or whatever it is that this point has to endure. Yes, if it's failure, then this one may be cut off from the base, and you want to know, okay, it's cut off in point D. So let's check in point D to the original design. How was the force? Like that. Yeah. And for quality, if you know the force or the moment, then you might want to continue the design. So what kind of welding should we put? What kind of other mechanism to attach this part and this part? Is it glue? Is it welding? Is it screw? It could be anything. But each of those joints has different capacity to endure this moment stress and strain and so on. Yeah. So that's related to product development and also quality assurance and also post use of cell. When it's a failure in the market. Yeah. So that's usually the basic of this. You're gonna collaborate with some other people from mechanical engineering, maybe civil engineering, that they have even a more specific software to check. But the basic principle is still using this formula. Whatever the software is, still using this. Right? Moment. M is equal to F multiplied with T. Okay? Alright. So let's do this then. Let me check. But for this case, you have 50 toward the x-axis, and we have 20 for this force. Question is the moment of force in here, or short, depend on how you approach that you use. Yeah. You can decompose this or use it exactly. If you use the actual length of the arm, maybe it's a bit long because you don't know how some step that you need to do. But if you decompose this into Fy and Fx using the calculator, you know that you can use this Fx to calculate the moment. While the Fy it has no arm, because the line of the force of Fy is going through or from while the Fx is the 3 meters is the arm. Yeah, that's the principle. And x and y, I put it this is x, this is y. Why not? Who told you that x has to be always here? It has to be here. We could change it. If you remember in AutoCAD or in engineering drawing, you're the one who take care of where is the x, where is the y. I know in here this is the x, this is the y. But why not using here? This is the x, this is the y. What is that? Why not? Okay, so this is the x. Sorry, this is the y, this is the x. It's okay. Right? This is just drawing. You can look straight or you can look like this. Still the same structure. Alright. So let's continue. You can try this at home and see yourself as a practice here. Now I want to explain about this couple copling. It's additional concept which is followed by two forces acting on an object with the same magnitude, which means same Newton, same magnitude, but opposite direction and parallel line of action. Let's see in the next page about the picture. This force, when multiplied by the distance, will form a moment of the couple, called the moment of the couple or couple moment. This is the picture. Well, it's like this. One F is going to the left, the other F going to the right. Yeah, and each of them is parallel to each other. It's not like this, but exactly parallel. And the same magnitude, which means same Newton. This is a couple. Yeah, a coupling of couple. But then, toward the point A, then we have this. We have, based on this, we have the distance between this F, one here. We have point A, in this case. With point B is in the distance in between F top and F bottom. Or S1 and S2, the distance of the point B. And we have this D1 and D2, which is the distance between the top F to the point A, and the bottom F to the point B, from point A as well. So, moment that occurs at A due to F, and there are two F, just simply actually you just need to use the resultant here. Yeah. MA is equal to F multiplied with D1 minus F multiplied with D2. So in this case, I think it's using this. I think because F multiplied with D1 is plus, F multiplied with D2 is minus. F multiplied with D1 is F multiplied with D1. So because of this F, it has rotation effect clockwise. So, and it's plus, so I'm guessing this one. While the F multiplied with D2, which is F multiplied with D2, is minus. So, because the rotation effect is counterclockwise. And since we have this, then if it's the other way around, that means it's going to be minus. So, I'm guessing that. So then you calculate this, if we have the scalar or the magnitude that we know. But then we have another question, B, in point B. Yeah, what's the moment of point B because of these two F? We have this F multiplied with S1 plus F multiplied with S2. Both for point B has an effect of clockwise rotation. So that's why both are plus. Yes. Plus, plus. Yeah. So, or yes. And we have MA, we have MB. Okay. So couple moment. K is F multiplied with D in this case, so this. MA is equal to MB is equal to MK or any point. That's a couple moment. It should have the same value even viewed from any point. I mean that's the idea of coupling moment. Yeah, the principle. And then from here we have something else which is called replacement coupling. For example, as this. a couple can be replaced by another couple as long as the sum of the couple moment is the same. So the main point is the couple moment has to be the same. Yeah. If it's not the same, then it's not a replacement and it's not couple moment. If this is not like this, then it's not couple moment. Yeah. It's not the same. So here, for example, we have P on the to the right, this P to the left, and between them we have a distance of D. And if we decompose this P and this P to the axis, we say what? This is x-axis, this is y-axis, which means this is y-axis, this is x-axis, negative x. I mean, yeah. Is it correct? No. Sorry. If this is y, this is x plus y plus. This means this is x minus. This one is y minus. Yeah. On the axis. If we decompose this, we have this. Both P of the composition of the original P in x and y axis here. Here P accent and P double accent. So this one P double accent and P accent and P double accent. And we know the distance Q and R in this case. So P accent and P double accent are complements of P which with distance Q and R. So M couple is this one, P multiplied with D, which is P accent multiplied with Q plus P double accent multiplied with R. That's the couple moment. In this case, yeah. R. In this case, which P? Q is this Q, this is R. So P accent is this one multiplied with Q, and P double accent is multiplied with R. Yes, I think it's the point, the effect of the couple moment. Yes, and then if you calculate it, then you can have the result. And another example, but this is in Indonesia, I didn't get a chance to translate it. Let me explain to you. A and B, here you go. We have R going here, and other R to the bottom going to the left, down corner. So if we decompose this into N and W, also here into N and W. Again, this is showing the coordinate that is X and Y. Say N is in X-axis and W is in Y-axis, for example. So also well. So you can see from here, the W is going in the same line in the opposite direction. That means this 2W, since this R and R is the same, this 2W should be the same, and it if you add it, it's going to be 0. So what's left is just the N. Just the N with the distance as S. So moment, couple moment, we can just put it like this. N multiplied with S, that's all. Yeah. Here. For this picture, we need to calculate M couple as R multiplied with T. R using R multiplied with T. Because T is the distance between here, this point, and this point, but perpendicular. So it's not exactly this S, but this T, this direction, somewhere in here, or here. But for the B picture, then we know that this S is already perpendicular with the end. This is 90 degree. 90 degree. So we can just use it like this. Okay? This is a couple for this condition. By having the component of the force, you can have a shorter calculation. Another single couple or resultant couple, if we have this force, several couples can be made into resultant couples if the effect on the object remains the same. We have this as a couple, and then this one is another couple, but then we can make a resultant couple. It's equal to this, or equal also to this. So how these things work? How come? We still have this B, which we maintain here, same B. But we have this G that we move into here. The thing is that if we move, we need to know what is K, because this has different direction. But if we can calculate it, if the couple of G, capital G multiplied with small g, we can have the same as capital K multiplied with B, then it's fine, because we find the couple. This is the couple, and we can find this works. So as well as here, we maintain the G in here. We just need to move this couple into here, from B to L. Okay, from B to L. G multiplied with capital B multiplied with small b equal to L, capital L multiplied with G. That's a resultant couple, or adding couple, and could be different way. In the middle or the right side. And if we already have it, then you just need to calculate, because in here we have, for example, L and G. Right? Now we have capital L and capital G. You just need to add here. For the resultant couple, force U is the sum of two couple G and L. So if we have this on the right side, we have G and L, we just need to add G and L, become U. Yeah. G and L become U. Here. Capital G multiplied with small g plus capital L multiplied with G, in this case, equal to U multiplied with G. Or G plus capital G plus capital L equal to U, because we take off all the G. Okay, this is theory again. That's the end of the question though, this time. This is still theory, not yet example. Another theory, transfers of force and control moment. Among these are the ones that you will use quite a lot, including in session 2. Now this is session 1. Session 2 you will use this quite a lot. Yeah. When you read it, the force acting on an object at a point of action can be transferred to another point of action outside the line of action, provided that the new point of action has its moment couple item. So here we have this couple. No, we don't have this. This and this. Only this, yeah? And then we want to eliminate this. Not to eliminate, but move this from point A to point B. So in this case, we can move this F into here. And then, because this F has a moment, in point B that has an effect clockwise rotation, this F. Then we put like this. We move this F into here and we put it like this. Yeah. You need to draw this. So that's the kind of move, transfer of force and coupled moment. So we transfer that force into. Now after you have this, you don't need this point A anymore. There. Okay. So that's the purpose. There. The point of action, I'm going to read the bottom parts from section. The point of force, the point of action of force F at A is moved to point B. Yeah, move to point B by adding couple moment M equal to Fg at point B. There is a moment, additional moment. Okay, there. And here, this is another example. In the A, we have three steps. First step is we know what forces that we have. We have in this case 4 forces. P1, P2, P3, P4. Yeah. And each of those forces we know the arm. This is the arm. If R1, R2, R3 is the arm of the F. In this case, we move the P1, P2, P3, which is everywhere in this shape, to the point A. So when we move, for example, P1 from here to point A, we have this. But since this P1 has an effect, rotation effect, which is clockwise in point A, we add this M. M1 we can call it. The other one also as well. Yeah. Say P3. We move P3 to A. Let's P3 here. Yes, but then we have moment because of P3 effect is counterclockwise. We have M3. As we move this, we have M3. The M3 is here. Yeah. Since P2 is also parallel to P3, we have F2 here as well. But the moment M2 is clockwise. M2 is here. This M3. So because of this, then we can add all this moment and there is one resulting moment M. Yeah, with the resulting force of R in point A. So point A need to endure force of R Newton and the moment of something. Okay. Here. Any question? This picture is a bit small. Yeah. You can see it clear. Now, in figure C or picture C, the resultant force acting with a non-zero coupled moment shows that the point of action of the resultant force is not at point A. Which meaning, actually, if you have this picture, where is R? Since we already, this is the original force everywhere. It's in each location. When we move it to A, and we have a resultant force, this is actually not where the R is. This is not the actual R is. It's just that we move every other force to point A with this M. So if the question is, where is the R actually? Then with this moment data, we can find where is the R. Here. We have S. Yeah. How do we know? We have M. If we know M, say M is 100, for example, and R is 50. So if M is 100, M is equal to R multiplied with D, right? If this is 100, we know this is 50. What is D?
2.
Is 2. So R is here, which is, or S in this case is 2. Okay, here. But the direction of R is still here, and it's clockwise. So where is this 2? If we have this point A, we have R in here, and here as the M, we know that 2 is D. Where is this 2? The original resultant force has to be still the same. Still this direction. So where could it be? Could be in here? Or could be in here? Is it the R? Is it the R, the original place? I mean the actual place, not original, actual place. If we choose this one as the R from point A, it's going to have an effect of counterclockwise, different than this. What we need to find is the clockwise direction. So it has to be this. This is the actual R, and this is the D. This is how to find where is the actual R. Yeah. Or in this case it's S. Yeah. That's I know this is like, if it's long, why should we do this? But it's actually when you have not just 4 forces, but much more. This 4 is actually easier. Okay. Say you have 100 F, then you might want to do this better than calculating each forces. Okay. Any question? Right. So this is another example. We're just going to discuss this in 5 minutes and then we're going to finish. We have this shape A, B, point A and point B, and we have this shape, rectangular shape, and we have some data about the distance between D and B, 18 centimeters, C and B, it's 70 centimeter, and F and where's F? Okay, F A is 40 centimeter. And we also have this side lateral, which is 100, which means it's 100 centimeter in the distance. 100. Determine the resultant force and the single moment that occurs at point B. So we want to look at point B, not point A, specifically B. For example, where is the position of the point of action of the single force in relation to point B? So it want to ask the force in point B and the moment, single moment in point B, and then after that is asked where is the actual location of resultant force from B. Yeah. For this, you simply decompose this F that is in 60-degree angle, 60 from the y-axis. This one you don't need to decompose, it's already in X, into this. calculate it using your calculator. Say we keep it like this. This one is 80 Newton. Now we have how many forces? 1, 2, 3, 4, 5 forces that we can move to point B. Here. Say we want to move this F to point B. We will move it here. We have this F. We move from here to point B. But then, because we move here, we need to check the effect of this force in point F to the B. It has clockwise rotation effect. So this moment is to be like this, which is this one. Oh, they didn't put the name. But they should put the name. M1 there. Yeah.
When can I know when the direction is in counterclockwise?
From point B, this is counterclockwise. This is clockwise. So this one is clockwise, point B. This one is also clockwise. This one, there's no arm at all. Because the line of force is from B. This one, if we move this force here, and going up, it's going to have clockwise as well. So here, we move this here, it's going to have counterclockwise. And this is where you need to put the line. Yeah, so maybe you need to calculate the counterclockwise first. Okay, the F is still there, plus the moment. So point B has this endure all those forces, 1, 2, 3, 4, 5 force, and the moment that is created by the location of that forces. Yeah, it's just like this M1 and 5. I don't know which one is 5 and what is 1 like. Say M5 is this, then M5 is 80 multiplied with this distance. Okay, there. If we do that, and we multiply all the M and we'll add all the F, we have this. Okay, I need to take a call. Sorry. Try to understand that. Yes, we can add all the F, Fx, Fy, all the X and all the Y. Remember, the plus and minus is plus X minus X, the direction, and this one as well, the direction of the F. Y is plus, everything is plus. So then we can calculate the resultant of the force as well as the resultant of the moment. Here. Yeah, resultant of the moment, result of the force. And remember, the moment, there is one that is counterclockwise, so one is minus. Yeah, the other is plus, but one is different than the other, which is M4. Yeah, M4 is different direction. The other are clockwise, while the M4 is counterclockwise. That's why we have this minus. So now we have the resultant, we have the moment. Okay, and now after that, since we know the resultant, we found out the direction of the R. Based on the Fx and Fy, we find the R, and then with the tan theta, we know the theta in this case. So we know where is the R, this theta. And don't forget that we also have this moment, so we do have this R and moment. R was 139, the moment was 80. 139 and 80. So therefore, we need to find the S. S is found out to be So if S is 57, we have M and R. Where is the actual R? The actual one. As long as we keep the effect of clockwise rotation, if we move R in here with distance S, then we still have the clockwise. So this is the position of R from point B with S. R. Still the same direction with the previous R. But this is the actual R from the all other F. So all other F here, not this one, the original, yes, this one, all these three are, if you calculate, it's going to be here. From point B here. It's going to be here. Any question? Here, you decompose, move it to point B, that's being asked, and then calculate all the M, all the R, all the F. You have R and M, sigma M, sigma F, and then the direction of R with the theta, and then find the actual R based on this. And that's it. That's finished.